Hello, today we are going to discuss momentum and collisions, which is part of chapter 9 in your textbook for physics. So before we can get started with momentum and collisions, we need to review a few key concepts that we've already covered. The first review statement that we have is that an impulse is created by an external force acting on an object over a certain time interval. And the equation that we had for this was that impulse, which is a capital J, is equal to force times the change in time. An example of this is if there's a stationary soccer ball and you go to kick it, the force that your foot applies to the ball times the time that your foot is in contact with the ball is equal to the impulse that is imparted on the ball. The second review statement that we have is that an impulse causes a change in the momentum of the system. So the equation for that is that impulse, capital J, is equal to the change in momentum, which is P. Now notice both impulse and momentum are given the vector symbol, and if we go back to the first equation that we had, impulse and force are vectors. The change in momentum can also be written as the mass times the quantity V final minus V initial. So that's the change in momentum, because remember, let me pick a different color here, that momentum is equal to mass times velocity, and both momentum and velocity are vectors. So if you kick that soccer ball, then the soccer ball is going to start moving. It's going to change from rest to having a velocity. All right, so we decided that each day as part of our lecture, we're going to try to find a sample problem in our final exam study guide to go through. So today we chose problem number 62 on your final exam study guide, and we took a look at it. So problem number 62 says a 0.12 kilogram ball is moving at 6 meters per second when it is hit by a bat, causing it to reverse direction and have a speed of 14 meters per second. What is the change in the magnitude of the momentum of the ball? All right, so let's list the things that we know. The first thing that we know is the mass of the ball is 0.12 kilograms. And then you ask yourself, is that an acceptable unit? Well, mass is supposed to be measured in kilograms, so that is fine. It is moving at, so the initial velocity is 6 meters per second. Meters per second is an acceptable unit for velocity. When it's hit by a bat, causing it to reverse direction, which is important, and have a speed of 14 meters per second. So the final velocity here is going to be negative 14 meters per second. The reason why we call it negative is because it's in the opposite direction. So velocity is a vector, so direction is very important. So we are supposed to find the change in the magnitude of the momentum. So delta P. Delta P is equal to mass times the change in velocity here, or we could write that as mass times the quantity V final minus V initial. So if I take a look here, I know mass in both of the velocities, so I can start plugging in my values. I'm going to take the 0.12 kilograms times the quantity, negative 14 meters per second, because it's always final, minus the initial, which is 6 meters per second. And when we do that, I have that we get a value of negative 2.4 meters per second. Which if you look at your options, there is no negative, hold on, I messed up those units. It's not meters per second, it is kilograms times meters per second. And if you look at your options, none of them are negative 2.4, but it does say the magnitude of the momentum change. So the magnitude is like the absolute value. It's the quantity without a direction. So option D is 2.4 kilogram meters per second. So that is the correct choice. Now, Today we are going to begin discussing collision types. Collisions are when two objects interact with one another. There's three major types of collisions. The first is called an elastic collision. Elastic collisions are one in which the objects involved bounce off one another or ricochet. There's a nice French vocabulary word for you, ricochet. When these objects bounce apart, there is no loss of mechanical energy. Now, your textbook saves mechanical energy for the next chapter. But just kind of an overview, because the class that we're in is called classical mechanics. So mechanical energy is sometimes abbreviated as ME, and mechanical energy is kinetic energy and potential energy combined. Kinetic energy is the energy of motion. Potential energy is the energy associated with position or shape. So kind of the energy associated with how high an object is due to gravity. We call that gravitational potential energy. There's also due to shape, like if you take a spring or a coil and wind it up very tight, then it will have a higher potential energy. Regardless, when these objects bounce off of one another, the kinetic energy of one object is transferred to another object. A prime example of this would be like if you're playing billiards or pool, because the balls will just hit one another and bounce off of each other. That's the object of the game. Inelastic collisions are the second type. Inelastic is a collision in which some kinetic energy is transformed to some other type or source. So maybe there's heat that's given off, or even light, like some sparks, some friction, some sound, some deformation. So like if two cars collide and one car gets crumpled up, then it is deformed. I do want to tell you that inelastic collisions are actually the most common in real life. Because if you think about it, anytime you have two objects, even billiards that will collide, there's usually sound or friction involved, so there's a slight loss of energy. Just kind of like in projectile motion, a lot of times we're going to simplify things and consider that certain scenarios, like when you're playing billiards, are elastic collisions, when truly they're not, because you're losing a little bit of energy to sound and heat and friction. But inelastic collisions are more difficult to deal with mathematically, because you have to keep track of all of those little ways that you're losing kinetic energy. So we tend to simplify and stick to perfectly inelastic collisions when we're learning about this. A perfectly inelastic collision is a collision in which both objects stick together after a collision, so they are going to become entangled, or they're going to move as one unit afterwards. Now, I do want you to note that kinetic energy is not conserved in an inelastic collision. It's only conserved in the elastic collisions. However, our huge new statement today is that no matter what type of a collision that you have, momentum will always, always, always be conserved, which gives us a new equation to add to our equation sheet in our toolkit, the law of conservation of momentum. The law of conservation of momentum is a typical law of conservation in that it says, under ordinary conditions, momentum can neither be created nor destroyed. It can be transferred from one object to another. So our first equation is that the PF, or the final momentum, is equal to the initial momentum. But I do want you to recognize that this is like a sigma sum type of a momentum. It's the total momentum for the entire system. So you can add that to your equation sheet. We also have two separate equations, one for elastic collisions, one for perfectly inelastic collisions. So remember, in an elastic collision, you have two objects that are colliding and bouncing apart. So like cue balls that are going to interact and then move apart from one another. So the equation for an elastic collision is the mass of the first object times its initial velocity plus the mass of the second object times its initial velocity will be equal to the mass of the first object times its final velocity plus the mass of the second object times its final velocity. Lots of subscripts going on there, but it hopefully makes sense to you what those all mean. Now, a perfectly inelastic collision, remember, is where the objects combine and move together as one unit after the collision. So the equation for that is much like the elastic collision, but it simplifies a bit. So you still have the mass of the first object times its initial velocity plus the mass of the second object times its initial velocity. But in the end, these two masses are now combined, so we take the quantity m1 plus m2 all times a mutual final velocity. So let's do a couple of sample problems. Our first sample problem says, two ice skaters, Sandra and David, stand facing each other on frictionless ice. Sandra has a mass of 45 kilograms and David has a mass of 80 kilograms. They push off from each other. After the push, Sandra moves off at 2.2 meters per second. What is David's speed? All right, so let's list the things that we are given. If this is David and this is Sandra in our diagram, we know that the mass of Sandra is 45 kilograms, and kilograms is an acceptable unit, so that's okay. The mass of David is 80 kilograms. We know that the initial velocity of Sandra is 0 because she is standing still. Same thing for the initial velocity of David. Now, at the end, we are told that they push apart from one another, and the final velocity of Sandra is 2.2 meters per second. Now, if you think about it, David is probably also going to have to be moving. He can't stand still because the total initial momentum was 0 since they were standing still. So he's going to have some momentum that cancels out the momentum of Sandra. So we might even hypothesize that David is going to be moving in the opposite direction to Sandra, but we don't know what the final velocity of David is. So this is an elastic type of a scenario here. So in the beginning, we had the mass of David times the initial velocity of David plus the mass of Sandra times the initial velocity of Sandra is going to equal the mass of David times the final velocity of David plus the mass of Sandra times the final velocity of Sandra. Now, this is helpful since this is our first true equation for collisions. However, the initial velocity of David is 0. The initial velocity of Sandra is 0. So we can actually greatly simplify this equation and say in the beginning, there was no initial momentum. In the end, though, we do have momentum. So this part of the equation is going to remain. We are trying to determine the final velocity of David. So if I'm trying to isolate that, the first thing that I'm going to do is subtract the mass of Sandra times the final velocity of Sandra from each side. So this now is going to say negative mass of Sandra, final velocity of Sandra equals mass of David times final velocity of David. And if I'm trying to get the final velocity of David by itself, I'm going to divide by the mass of David on each side. So if I clean that up a bit, the final velocity of David should be equal to negative mass of Sandra times the final velocity of Sandra divided by the mass of David. Now I can plug in the mass of Sandra is 45 kilograms times her final velocity of 2.2 meters per second all over 80 kilograms. And when I solve that, I get a value of negative 1.2. My units would be meters per second because it's velocity. Now let's stop and think, does this value make sense? Why is it negative? Because he's moving in the opposite direction to Sandra. Is he moving faster or slower than Sandra? Well, Sandra was going at 2.2 meters per second. He's going at 1.2, which is slower. Does that make sense? Well, it should make sense because David has more mass. So more massive objects are going to have to go slower in order to have the same velocity as a lower mass object. Second sample problem here. The best way to get an old-fashioned wooden sled moving is to take a running start and jump onto it. Bailey decides to give it a try. She runs at 4.0 meters per second and launches her 26 kilogram body onto a stationary 5.9 kilogram sled. How fast is the sled moving just after she lands on it? All right, so in the beginning, we have the mass of Bailey times the initial velocity of Bailey plus the mass of the sled times the initial velocity of the sled equals. This is an inelastic collision, a perfectly inelastic, because Bailey and the sled are together moving with one final velocity. Now, if I list the things that I'm given, I know that the mass of Bailey is 26 kilograms. I know that the mass of the sled is 5.9 kilograms. I know that the initial velocity of Bailey is 4.0 meters per second, and the initial velocity of the sled is 0 because they called it a stationary sled. So if I go to my equation, this whole part is going to cancel out to 0 because the sled is not initially moving. We are supposed to find the final velocity. So if I take this equation and rewrite it, mass of Bailey times the initial velocity of Bailey equals the mutual mass of Bailey plus the mass of the sled, all times the final velocity. And if I'm trying to find the final velocity, then I need to divide both sides by the quantity mass of Bailey plus mass of sled. So if I rewrite this, the final velocity should be equal to the mass of Bailey times the initial velocity of Bailey, all over the mass of Bailey plus the mass of the sled. So the mass of Bailey is 26 kilograms. Her initial velocity is 4 meters per second. And the denominator, I'm going to have 26 kilograms plus 5.9 kilograms. Now, the number one place that I see people mess up on this is they forget that that has to be a quantity total mass in the denominator. So, the final equals, I have 3.3 meters per second. Now, if we look at this, that's a slightly slower speed than 4.0 because this is a more massive object as they are moving together mutually with one another. I hope after this lecture you understand the differences between elastic and inelastic collisions, and I hope that you understand that regardless of the collision type, momentum is always conserved.